Yeah, so just to confirm, you can see my screen and everything, right?
Yep.
Okay, so yeah, let's get started then. This is the first meeting for the Algorand Community Study Group. It's a very long name, but for now, it's all we have to make do with. So I go by this name, Hash Maps Data to Value. I'm a digital community champion or ambassador for the Algorand Foundation. I'm organizing this. So it's here. Yeah, welcome. So first of all, yeah. So first of all, I just want to mention, like, okay, study group, like, why do we have a study group, or what's the point of this? Well, the foundation is working on different education-oriented ventures to educate people. Primarily, educate people who are developers who would be interested in doing stuff with Web3, and specifically on the Algorand blockchain. And yeah, I mean, that's a huge group. I mean, there are a lot of developers out there, and we would want to capture at least a small amount of them and bring them to Algorand, right? But then there's also this other step where you could be a Web3 developer and do some very basic things, or yeah, I say basic, but kind of, I guess, scratching the surface of what you can do with cryptography. But to get to that point, you need some more, like, yeah, you might need some more math knowledge or applied cryptography knowledge. And so I figured, well, why not? I'm interested in that, and why not create a study group so we can educate ourselves and elevate ourselves, and also make use of the Algorand blockchain and the computational resources that are currently underutilized. So yeah, that was the idea behind the study group. And primarily there's a what do you call it, a channel or whatever on the official Algorand, Discord server. We also have a GitHub repository where I'll be uploading resources of various kind. So yeah, I invite you to take a look. With me is Kappa. I don't know if you...
Yes, Jacobo, you can call me.
Yes, Jacobo. Yes. If you're fine with doxing yourself.
Yes, it's no problem. So I'm still a student at the University of Milan. And was very interested about this study group, and I hope we can dig in the most topics we can. And yes, I'm very interested in into these topics. So
yeah, I'm super excited to have Jacob here with me. I mean, the point of the study group isn't I mean, the point is that we're all supposed, that we're all going to learn collectively and like pick different topics or different resources for those topics. So for this topic, I figured the first thing we could look into is elliptic curve cryptography, which is kind of the basis for everything. And I figured we could use this. There's this book called A Graduate Course in Applied Cryptography by Boneh and Victor Shoup. And Dan in particular is very famous in the crypto community. And he has had many talks and many presentations. So I really invite people to look him up. He also actually has a video on pairings, which we'll cover also in this presentation. And the introduction for that talk is actually given by Tal Rabin, who is a researcher at the Algorand Foundation. So yeah, it's a small world.
yeah.
But yeah, so in this case, we're two people, and yeah, I'm really happy to have Jacob here with me. And in this case, I made this presentation, and I'll be presenting my thoughts and notes. But in the future, I'm hoping also that there'll be more people coming on, and more people to present and share their notes. So yeah, so let's get started. Yeah. So this is the agenda I presented for this meeting, and it follows the various sub-chapters or subsections of chapter 15. So we'll be going through them, and I have my notes from those sub-chapters and summaries. Here in the middle, I added this intermission. So there's this pull request right now, and hopefully soon it'll be merged in to the Algorand official repository, so for the Algorand node software, which will add more elliptic or EC math capabilities to the AVM and make some of the things we'll be talking about here implementable as Algorand or in Algorand smart contracts.
Sure, because right now, which are the ones supported? Only the AD 250, the 125.5.9.
Exactly. Currently, there are signature checks you can do. So you can check if someone, so you can check like if someone have used a ED 25519 public key and a private key to sign a message of some kind, and then you can check that signature. And you can actually do a lot with that, but there's a lot more coming, a lot more elliptic curve math, addition, scalar multiplication, pairings check. So we'll cover that later.
That topic is very interesting for me. So because I want to understand where does it scale to? What's needed for what? What's the target that you can reach?
Yeah, and we also have we'll come back to it later, but basically like with this PR we could do pairing checks, and with pairing checks we could validate certain ZK snarks, which are incredibly powerful. And we actually already have a demo repository made by the foundation, and I don't know exactly, I guess at least
the one that shared Barney, yes, the one that shared.
Exactly. Or just shared it, that it's the DevRel team, I suppose, and so you could verify ZK snarks, which is it's going to be very important in the future. So if we look at, I can share. I do have the book itself here. So it begins here, and there's an intro, talks a little bit about some things. And so first we can kind of introduce, or what Dan and Victor do is they introduce what an elliptic curve is. And they actually go way back into history to talk about this guy named Diophantus from the ancient times. And he defined, or elliptic curve, you can define these types of equations that describe them. And here we have, I call it rational, meaning that X and Y are rational values. You can kind of see them as, they're like, they can be decimal, they can be whatever type of values. So you get these curves that are curves. They are full, they're lines, basically. They're not points, individual points. There are infinite amounts of points. So this was first defined back here. Like, there's some history in the book, if you can read it. And so there are points on this elliptic curve, X, Y. And interestingly enough, there was this idea of like, well, how can you easily find more points that satisfy? And especially if you're interested in not rational, but I guess specifically like integers, let's say. And there were two methods that are identified: the chord method and the tangent method. So I can mention this here. So what you can do is we introduce this concept of an operator, a point operator, or you can call it point addition, which is where you have 2 points. Here you can define, using the chord method, you can take 2 points and you can define another point. And using the tangent method, you can take a point with itself and get a new point. So just visually, what it means is that, so for the chord method, what you do is, if you have P here and you have Q here, to get the P plus Q, what you would do is you would draw a line between or through them. And due to the shape of these curves, this line will touch the curve at only one other place, which is here. And then what you can do then is you can take the mirror of that, which is this point here. So basically, you flip the Y value.
Yes, because it's symmetrical on the.
Exactly, it's symmetrical. So you flip it, and so you would get P. So in this, using the chord method, you would do P plus Q, and then you would end up with this point R here. And visually it makes sense, I hope. And there are, if it sounds confusing, there are a lot of videos on YouTube where they show this like with animations and stuff. The tangent method is very similar, but what you can do is you can imagine if you kind of brought Q all the way down here to P, so that Q became P, and then instead of 2 points, it would be the line would be going through 1 point, and basically the tangent. It would do the tangent of the curve at that point. So it would go something like this, if you can see, and yeah, that would also hit the curve or intersect the curve somewhere, and then you would flip.
And get R.
Yeah,
Yes.
So yeah, so this is these group operations. And so in cryptography, we're interested in not the rationals, but we're looking at these finite fields, and particularly we're interested in integers, mod some prime number, mod some number, but specifically we like prime numbers. And so instead of these nice full curves, you would see points, right? And a lot of them, a lot of points. And we would also not see, like, this wouldn't be extending, the domain of this wouldn't be extending all for x and y to infinity and negative infinity, but rather to that prime number. And then after that, everything would just, using the modulus, you would just flip around. So if you can imagine this hitting there, and it would like kind of come here and then continue like that, and then it would at some point hit the wall here, and it would come out of here, and yeah, that's how it would how you would get a new point, a third point, using 2 points and adding them together. And in the book they have these different, they have a notation. So they denote, this is how they would denote an elliptic curve defined over a finite field, and specifically with P here, being that the same P is here. And we would have, and this is how they define the set of all points on the curve plus the point at infinity. So this is how they would define all of the points. So like I said, like instead of having those smooth curves that would contain all of the rational points that fit in to that fulfill the equation, you would instead have those integers that I mentioned, and this would give you a set of points, a finite set of points. And then we also we have this idea of point at infinity, which it's confusing in the beginning, but it's a point that we just add, and it will serve as a type of identity element. We'll come back to that. And in the book they have a different font, but I couldn't. Yeah, I wasn't. Yeah, I just picked a different font for the O. But yeah,
the O.
They have a specific point for the O. Yeah. And so here's an example of a curve, and then here with the ordered, or the prime here being 11, and then you would get these points. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, along with the point at infinity. So we would say it has 12 group elements. Sorry.
No. Sorry, just listening. I was agreeing with it. Yeah, sorry. No, because at first point infinity wasn't, so I didn't understand that part at first. But it's just like the empty element in the groups. Yes.
And especially like here we have, I mean, because here we have a two-dimensional view of it, but there's also another way that the different representations that you can use for the points, and another one is where you kind of wrap these curves or this curve on the surface of a sphere, and then it looks very freaky, but then you could visualize the point of infinity in a different way that makes more sense, I think. But yeah, it's just like an additional point that we add, and we have this operation. Previously I called it a point addition, but the idea here is that with the identity element you can do P plus this, and then you would end up with P itself. So it would be, nothing would happen. And what we do is we like to pick a point, and we call it the generator. So using just one of these points, you could imagine that you would so let's say that we have P, which is a point in in this group of elements, then using this operator with itself, so p, let's call it p, you will end up with 2p. And then if you do again, you can get up with 3p, 4p. And in fact, if you do p plus p, you get 2p. And then if you can take 2p plus 2p, you get 4p. There are ways of doing it this way. And you can generate all of the other points until you eventually end back to p. So we can call that point a generator. And like previously, I mentioned here plus, like addition. So we could call this additional. But you could also, another way of representing this operator is to use multiplications. And so if you have the generator point g, if we add it with itself a times, then we could end up with a times g, which is we can call big A. And then another way of looking at it is if you instead use the multiplicative notation, is that you would do a multiplications, and then you would end up g to the power of a. And so depending on like this is so I know this is very confusing, but depending on how you look at it, or depending on the context, you can pick which notation you want to use. So if you think about the O or this point at infinity, you could imagine that if you have G plus O, you would just get G, just like here. So then it would kind of be like a 0, right? Or another way of if you had it in this case, it would become kind of be like a 1. So you would take G times this, you would end up with G. So in that case, it would be like taking it times 1.
Okay.
And so these curves can take different forms. You can represent them in different ways. So I mentioned Weierstrass, Edward, Montgomery, and also like twists you can do. In the book they talk about this. So here, so let's say that we take a generator. So you can pick whichever one you want to pick, but you can imagine that it's a member of this elliptic curve, or the set of points on the curve. And that point is going to have an order q. So the elliptic curve is defined over a field, right? So the field will determine x and y, but then that doesn't mean that there's no question of how many points are there going to be that fit, like for that specific generator point, how many other points can it generate on that curve. So this is a little bit confusing. I was very confused by this for a long time. But so you have to kind of separate the orders of things. And so we could say, there is a group of points on this curve with order q. And if q itself is also prime, then we have this nice property where, well, it was kind of what I was mentioning, or maybe it's not exactly what I was mentioning, but you get this property where in additive form, you can take that value, q times, if you add g q times, you would end up with this point at infinity value. And after that, if you add it, so if you instead of q, you would have q plus 1 here, you would end up with q in brackets q plus 1 times g, you would end up with g then, because you can imagine it kind of loops around. Does that make sense?
Yes.
Yeah. And a similar thing here, that in the multiplicative form is, if you take to the power of q, you would also
power of q, yes.
Yeah. So that's the idea behind that. And then we also have this nice property, as they mentioned in the book, which is that we get the discrete log problem being hard. So the discrete log, it's kind of confusing if you're thinking in terms of additive notation, but it makes more sense in the multiplicative notation. And this idea that, okay, so let's say that we have this value alpha, and then we take it times g, we're going to end up with this new point a. Well, how do you go backwards then? Like, so if I were to present you with g and a, is it possible for you to figure out how many, like, what was the scalar multiplication that we did on g? And the point is that it's, this kind of a divided by g. And the point is that it's very hard. Like, it's actually, with non-quantum computers, it's very hard. Like, you basically have to brute force and try all of, you have to try you kind of have to iterate through all the numbers. And it could be like 2 to the power.
So that's why we use also big prime numbers.
Yeah, exactly. Another way of thinking about it is that, if you have exponentiation, is that then, yes, this is, if you have g to the power of alpha equals this new point a, we have to take log. Is it possible to take a log, or like does one even exist? And the point is that this is very hard, because it's just hard, because we're taking mod. I'm using the equivalent sign here, but it's because like things loop around, so we're using modular arithmetic here, and this is like the foundation for our cryptography, pre-quantum, and why we can use these words. So yeah, I'll mention it later, but yeah, so the scalar value here is what we usually use as our private key, and then this point here is the public key. But you have to be careful, and they mentioned this, and I think it's quite confusing in the books. At least I found it confusing, but basically depending on like the curves you pick, the curve and the various parameters that you pick. So for example, if the order of if the number of points that fulfill the equation for a final field equals the number of points that or the order of the field that we used, so the max value for x and y, then this is no longer like, it kind of break, like this no longer, like this is no longer hard, and so then you're in trouble.
Yes, that was actually one thing that I was a bit, I didn't understand really, because there are some curves that are easy to break, or some points in the curve that are easy to break and some that are not. So
yeah, or it's like if the number of points, if there's basically a unique points on, like if there are as many integers in our finite field as there are points on the curves, how I see it, then the discrete log is no longer difficult. And they don't really explain why, and it's kind of confusing, and it's not really that important, because in practice we just pick, like we're not going to do our own crypto. We're not going to invent something new, at least not at this level of our of our knowledge. We just pick whatever is available. So this is already covered for, but they're basically explaining like, well, there are ways in which all of our assumptions, there are scenarios where they don't hold. And another example is where if there's a small integer tau, such that the order divides, basically divides this value, like it, then it's somehow it just breaks our assumptions. So we just stick to standard curves, and so there's something called P256, and it's very shady, or I think some people use it, but it's just kind of shady.
It was used. I said it was used, but in the research paper at the end, it was only given a seed, a specified seed, like written inside by the NIST, and they said, okay, this is the seed. You can then use SHA-1 on it, and you get P256. But since it wasn't explained, it's easier to stick to the curve, the next one, basically. The one
exactly. So if you want to trust them, you can trust them. And then there's another one, curve 25519. The other ones as well, but this one is the important one for us. It's the one that's used in Algorand.
But was this actually started in 2015? Or
so this was the paper. There's a paper. There was a cryptographer. I forgot his name. Was it Rubinstein? No, I forgot his name. But yeah, he released a paper. Was it 2013 or 14? I think. Okay. Where he kind of posted like, well, this is how I came to this. How I figured out this
curve, and then
I forgot. I should have remembered that, but it doesn't matter. And then we have what's known as ED25519, which is a signature scheme based off of this, and it uses twisted Edward, so basically a different form. They call it like birationally equivalent or something. So it's like, this is a one form of the curve, then you can twist it. You have a twisted Edward version of it, and then you get a different curve. Or a different form of the curve. So they don't, sadly, I think it's unfortunate, but in the book, in the chapter, they don't really mention ED25519 or what it is. But I've added more notes on the signature scheme, because there's an opcode in the AVM called ED25519 verify, and allows you to verify that these signatures. And it's also what we're using, when you sign a transaction on Algorand, it's what you're using. You have your private key, your private value, and then you have your address, which is a function of your public key. And then, you sign a transaction on behalf of your address, which has algos using this scheme. And you might also see it like if you're setting up your GitHub account and you want to use SSH to commit, commit your changes and git push and all those things, then if you see this ED25519 show up, that's where this comes from. So on the GitHub repository, I have explained how this works, and we might cover it in a future meeting, like just in more detail. I have this project or this thing. I haven't done much with it, but I just defined this protocol that inspired by other people that would allow you to do atomic swaps from Algorand to Monero. And then
the one you showed me. Okay, I remember.
Yeah,
that's very interesting.
And it would allow you to do that kind of atomic swap between Algorand and Monero by you kind of locking up. You're taking 2 points and adding them together, you get a third point, and then you just have to share. So if I have the private key for one of the points, and if you, Jacobo, have the private key for the other one, then we can like send money into this third point, but then none of us can access it until the other one gives up their private key. So I use I use this for that. So, like I mentioned before, the scalar here would be the secret key, and A is the public key. Another thing that you can do is, or that we sometimes do, is we see like this kind of entropy, like you have this random number, and then you hash it, and then or you do something with it, and that becomes the basis for your secret key. And that's another way of doing it. So it's that you don't really store the scalar, but you store some other thing that you then hash, and it serves as the foundation for this value. But the point is that this is the secret key, and this is the public key. So that's the basic for this basic elliptic cryptography. And after that, they start talking about pairings. And sorry, I'm just looking at the time. I think we have a couple minutes before.
Already? Okay.
I got some kind of notification.
Okay, maybe. How do you know when we started? Or?
I think it's fine. We have a couple minutes, so we'll just continue.
Okay.
And then
it says that. Okay, 10 minutes. Yes.
10 minutes. So this is chapter 15.4, pairing-based cryptography. This is where we come to pairings, and I don't know, Jacobo, I don't know how much you were able to read. Did you get to this part?
I actually used the Boneh presentation a bit to understand better this part. So I went over it to the end. So
okay, great. So I think like this is when it got kind of real or in some way. Like I think that's like this is kind of where you end up in some more magical stuff. In my opinion, I think you can do some really cool stuff with pairings. So this is the definition defined. I'm sorry for the wall of text, it just appeared, but this is the definition that you use. So if you have G0, G1, and GT, here I just want to mention here we're calling it G0 and G1, but in other contexts they say G1 and G2 instead of G0, G1. So I just want to mention that, like depending on, including in the AVM docs documentation, they also use G0 and they use G1 and G2. But the point is that these are 3 cyclic groups of prime order Q, where this is the generator. We can call for G0, we can call it G0. A big G0 is we can call it G0. So this is a point in G0, and similar here we have a point in G1. On the other hand, I just want to mention GT is not the elements in GT are not points. It's a finite. It's like defined over a finite field, but very, very big one. So a pairing is an efficiently computable function that takes you from G0, G1 to the target group. T stands for target group, and it satisfies the following properties. Right? So it's bilinear. So if you have 2 points in G0 and 2 points in G1, we have this relationship where with pairings where if you take u times u prime. In this case, it's multiplicative notation, but you could also use u plus u prime, and then comma v is equivalent of taking the product of these two pairings. So you get this bilinearity, and so that's the first property. The second one is that the value like this when we do a pairing, like we end up like we don't just get one. So there are some cases where if you do a pairing between you pair up something in G0 and G1. When you pair them up in the pairing function, you just end up with ones, and that's called like when it degenerates. So we have this property where it doesn't. So actually, this here is a generator GT that generates the entire group. Yeah, so I don't like this. Looks for me this is kind of confusing. It looks confusing when you see like this, but I think it'll make sense later. Sometimes so these are two different like the curve equation is the same, but the finite field that G0 and G1 are defined over are different. One is a kind of an expanded version of the other. In the case when it's asymmetric. So if G0 and G1 are actually the same, then it's a symmetric pairing, which is what we call a type 1 pairing. There are cases where there's even though G0 and G1 aren't the same, but there might still be some isomorphism that maps from G0 to G1 that we call a type 2 pairing. And then there's the case where there's no isomorphism between G0 and G1, in which case it's a type 3 pairing. And I think usually that's the kind of pairings that we use. So this is kind of, I know it's confusing now, but I think it's going to make sense later as we continue on. And yeah, pairings. I mean, in this case, we're talking about elliptic curves, but pairings exist outside of elliptic curve cryptography. Yeah, so G0 or the Q subgroup of this elliptic curve points. G1 is like I said, it's like also order Q subgroup, but for some expanded finite field where D is not zero. And the intersection of G1 and G0, so basically the point that they share is they only share the point at infinity. They don't share any other points. Yeah, GT is subgroup, but it's undefined. Yeah, but in this final field.
Yes, finite field. Yes.
So
Actually, I saw from the video of Boneh that if you refer to finite field FP star, I don't know what he meant on that, but I just get it. Okay, it's a subgroup of the finite field, I imagine.
Yeah, a multiplicative subgroup.
Okay, okay, it's multiplicative.
So
okay.
It is also larger, but yeah. I don't know. Yeah, they I think he used maybe a different notation there, or maybe yeah. But yeah, so here a lot of text here, but the point is that when we represent a point in G0, it's going to be smaller, like the amount of bytes that we need to represent it is smaller than the amount of bytes we need for G1. So G0 points are smaller than G1. And that's because we have this embedding degree, so that we use. And if D was much bigger, then it would just be G1 would just be huge. Like we would have to use many bytes to represent the points in G1. But so there's this compromise that they made. And this is also kind of, I think like in this chapter, this kind of they don't really go into too much detail on how they kind of derive this. You just have to accept that this is kind of how it is. And you don't need to understand all of this to use pairings. But this is what you need to understand. This is what I would call the central property. So when we have this is a point G0 to the power of alpha. This is a point in G0 and this is a point in G1. So even though like this is what the pairings allow us to do. They allow us to shift these secret values, these scalars across. So what you can do is here, like if you have a point, if you take alpha times G0, if you can, if you put in a pairing, you can shift that alpha over. So you can shift it. You can, like, here you can see that we swapped them actually. And here we can see that we actually took out alpha and beta. So this here is the generator for GT as a value, and we just take that value to the power of alpha times beta. So so we're basically getting you can call it homomorphic multiplication, or kind of we're multiplying encrypted or committed values, you could say. Because if I just give you, like, I can give you this point, but you won't know what alpha is. You would just see a point, right? Unless, like, it will be impossible for you to know how, or with very, very small probability, for you to know what alpha is if I just give you a point like this. It's just going to be like, yeah, X value and Y value. Same here for beta. But because of the way that this pairing equation works, or function works, sorry, not equation, the way it works is that it will map, like, all of these map to the same value in GT. So that's the point. Like, this is the you know, oops, yeah, like, this is what we mean by this. Like, the pairing function, it maps. You put in a point in G0 and G1, and then it will end up somewhere in GT. But then different values, different points end up in the same place, and we can take advantage of this. And then the pairing function itself, like, it's not as important, like what's used. But I mean, yeah, this is an actual function. This is not some, like, usually we just use E like this, but yeah, if you're curious, look into real pairings, and there are variant state and 8 pairings, and yeah, we use this algorithm called Miller's algorithm, which allows you to efficiently evaluate this. And I think yeah, Dan Boneh, in that video that you mentioned, Jacobo, he mentions that Miller, was he arrested as part of?
Yes, he was. He said Whale. No, actually, he said about Whale, that he was a French mathematician, very important in the Second World War, but that's an issue.
Yeah, sorry, it was the Zoom meeting ended, and now we're continuing with the second Zoom meeting.
So we were talking about the two mathematicians. There was Whale that first came up with this, also the pairings equation, that he came up with it during his jail time in France, because he didn't want to contribute to the war part. So he passed 2 years in jail. He also wrote an autobiography about this, and he proposed to other mathematicians to spend 2 years in jail because it would be more productive.
Yeah.
But yes, state pairings are the one that he shows. And he also says that at first they weren't easily computable because they use an exponential, and so the times for computation are too big. Miller came up with a paper saying that there's a way to make them efficient, and that paper came up in 1984, but wasn't accepted by the committee to be published. So it wasn't released until officially released, at least. It wasn't officially released until 2004, if I remember correctly.
Yeah, or like officially included in a journal or something like that, which is a shame. Yes. Yeah,
yeah. So the basic for the computation of all these pairings wasn't officially accepted until later.
Yeah. So pairings, and this is kind of like this feeling that I got when I was watching that. Originally, people thought the pairings were bad. It's like, oh no, we have this weakness in our cryptography for elliptic curves. And why is that? Well, for symmetric pairings, there's something called, or there's this thing we call the decisional Diffie-Hellman, or decision Diffie-Hellman, DDH, which is this problem that we expect to be hard, but when in pairing friendly curves where we have symmetric pairings, it's no longer hard. Okay, so what is the decisional Diffie-Hellman? The idea is that we want our points to look different. Like we don't want anyone, like if I present the world with a point, right, with a group element, we can call it, or a point, we don't want anyone to know the scalar that generated that point, right? the scalar that we took times the generator point to end up with that final point. So let's say that we generate randomly alpha, beta, and delta, right? And then we take alpha and we take times beta, and generate a new point called, or sorry, a new value called gamma, and then we take we take that scalar and then we produce a point using the generator. So this is what I mean. Like if we have alpha times beta here, and we get G0 to the power of gamma, we want G delta, and delta has no relationship at all with A and B. Like there's no relation, or sorry, alpha and beta. There's no relationship at all. We want them to both look. We want G0 to the power of delta and G0 to the power of gamma to both look random. Like we shouldn't be able to tell that any one of these has more of a connection to alpha and beta. Like, and this is what we call. It should be possible, to decide whether delta or gamma are equal to alpha times beta. And usually this is the case. But with pairings, this is no longer the case. Because with pairings, we could put in G0 to the power of alpha, and then this point, and then we can check, well, sorry. So in this case, since G0 equals to G1, so both of these, both the first value and the second value of this pairing function are points in G0. So like if with symmetric pairings, we can do this check easily, and decisional, so this is no longer the DDH problem is broken, you can call it, because we can do this check. And this is not the same as taking, if gamma was equal to A plus beta, that would be different, because then that would be the same as adding or multiplying. In this case, we're using multiplicative notation, 2 points, right? And this is trivial. Like we can check. Like if I give you, G to the power of alpha and G to the power of beta, you can easily just use operated on them and end up with this new point, which is a function of gamma, because gamma is the sum of alpha and beta. But when gamma is equal to alpha times beta, then because it's a symmetric pairing, the DDH problem is no longer hard. So this is when we do stuff like this. Actually, like this is what we call it kind of like additive homomorphism, like, or homomorphic encryption for addition. You can kind of say. So homomorphic encryption is the idea that you can take two values, encrypt them, and then you can do some kind of addition on them, on these encrypted values, and it will actually be the same as doing addition on the cipher values. So there's a ciphertext, and then there's, what do you call it when it's not ciphertext? Clear text, I think it's called. So if you have clear text, right? So that's alpha and beta, like alpha plus beta equals gamma, right? But here we can sort of encrypt them by doing, by making points out of them, and we can use the operation on them, and we can still do on encrypted values. We can do this kind of mathematical operation. So with normal, before pairings, when we don't have pairings, we can do this kind of additive. We get this additive homomorphic encryption. But with pairings, we get this multiplicative homomorphic encryption. So that's why they thought it was bad. But then, so if in this case we have something called the Algorand encryption scheme, that becomes insecure in this case. But however, this is not the case for type 2 and or specifically type 3, or especially, you could say, the type 3 pairings, or the most efficient asymmetric pairings, where there's no, where G0 and G1 are not the same, and there's no isomorphism. Like there's no way to go in between them. In those cases, this DDH assumption still holds. So that's, Also, and they're very clear about this, we need to pick groups that ensure that the discrete log problem is hard in the target group. Because if it's easy in the target group, then you can easily do this. You can apply this, even though it might look hard for G0 and G1, by using pairings to end up in G0 and G in the target group. You can then break. You could then calculate the discrete log. So if we assume that this is easy in
So
GT,
it breaks the discrete log problem, so you can
exactly. If we assume that it's easy in
go
GT
back.
or in the target group, then we can always transform these. We can just put in this put this point here, and then because of this what I mentioned before, the central theorem, you can break out the alpha as a exponent for GT, and then it's no longer difficult. So just something to think about, but or not really think about, because we use standard curves. And here I mentioned BN256, it's sometimes also called BN254, and then there's also BLS 381. This is what they call it in the book. These are the names that we use in the AVM docs documentation. And so here you can see like the size of the group order in bits for Q. For the finite, is it? Yeah, sorry, no. Yeah, I think it's for the group order for the exactly. Sorry, for the size of the group itself. So like roughly how many order of points there are. So this number of bits.
So it's always 256?
For both of them, yes. Here we're talking about the group order, from what I understand.
Okay, the group.
And maybe someone will correct me after this when we upload this stuff. And then,
sure.
But I'm pretty from what I understand, this is like the order of magnitude for the points. So for the number of points there are that that fulfill the elliptic curve equation. But that's different from what the finite field that we use. So for x and y values, like what are the max values, right? And those are different actually. Okay, and that will also affect the size of our representation for G0 and G1. So like the size of, if I give you, like when you're constructing your smart contract in the AVM, then you need to know like, okay, so what's the size in bytes? Like
in bytes,
I allocate this many bytes, right? And so the keys will be bigger in BLS 381, which will give you more security, but but less. It's not as fast. It's not as fast. So there's something to think about when you're picking.
Yes, you have to pick the trade-off. So
so here we come to kind of the speed trick. So pairings also allow for some there's some tricks to be mindful of, or to know about. So first of all, we should know that exponentiation, because now we're talking on the multiplicative notation, exponentiation in G1 is the fastest, right? And they have in some benchmarks, they represent some benchmark. It's fastest in G0, and then in G1, and then finally in GT. So GT is the most expensive, right? The pairing itself, they also did a benchmark on that, on how long it takes. And okay, so what does this mean? So okay, let's say that I give you that you have to calculate one of these three. So you can kind of choose, like, okay, let's say that you have alpha, you know alpha, and then you get to choose, well, do you want to take G0 to the power of alpha and then do a pairing here, or would you want to do it G1 to the power of alpha and then do the pairing, or would you want to do the pairing here and then take to the power of alpha? Well, these will all result in the same value in the end. Like the pairing function takes you to the same place in the target group, the same value. But this will take, like, these cost different things in terms of exponentiation speed, computation speed. So there's something to think about, that it's cheaper to do.
It's easier also to always start with the G0. So.
Exactly. However, if you know that you're going to do a lot of these, for example, if you're going to do a lot of these, then you can pre-compute. Sometimes it can be faster to pre-compute, to have this ready, and then just have different alphas and betas. So, or depending on what you want to do, like it can be, sometimes it's easier to pre-compute the values and then just do the exponentiation like that. You have to pick and choose. Also, and this is kind of like one of the magic things about pairings, is that when you take products of pairings, you can aggregate stuff. So let's say here it kind of looks confusing, but let's say we have we have n equals 3. So let's say we have 3 G0 points, and then we have 3 G1 points.
Sorry.
Alpha, yeah, no worries. We have alpha, beta, and gamma here, and then we have delta, epsilon, and zeta down here. So when we take a product of pairings, which there are some applications where you need to do that. This is how you would do that. Take the product, right? And then what you can do is you can break out, because we can do the magic, we can break out the exponents like this, take them up here. And then, because now we have the same value down here, right? We just combine them and then we get this in the end. So, so basically, yeah, if you know the exponent values like this, you can save yourself a lot of troubles. Rather than doing 3 pairings like this, you just, or even like, yeah, 6 exponentiations, 3 in G0 and 3 in G1, and then doing 3 pairings, and then, yeah, the multiplications of those, you can just do 1 pairing, or just get the target group generator, which is what this is. And then, yeah, just do 1 exponentiation. So this is kind of like the magic, or this is one of the amazing things you can do with pairings. And this is kind of, yeah, I rotated it. It's kind of, it provides an intuition for how Groth 16 ZK snarks are so efficient. And we haven't really mentioned what a Groth 16 ZK snark is, but yeah, we won't do it here. But basically, the point is that you can speed up. Like if this is, you could, if we could use this, if we can use exponents to represent some, like a bunch of different some circuits. Okay, yeah, no, sorry, I'm just gonna stop there because it's too off topic. But yeah, it's just like really cool that we can do that. But yeah, it also allows us to do very, very fast signature aggregation. So, but yeah, but before we get to signatures, we're gonna take a look at this. This is what I mentioned was my intermission. So we have this
changes.
Yes, this, and I have it open here. This is the merge request, or sorry, pull request. Merge request for GitLab. It's a GitHub. So the pull request, and we're kind of waiting for it to progress. I'm not really sure what's going on, but I'm sure they're working on it. It's very hard. I also have my own request where I wanted them to add opcodes for ED25519. And privately, I've heard that they might do it in the future after this, but like as a separate merge request. And it would be great because it could allow what are known as ring signatures, but that's also topic or a subject for a different topic.
The Monero, the one.
Exactly, Monero. So, but yeah, but the point is here that we would have this new opcodes. Yeah, we have the documentation here for the new opcodes, and like I wrote in the presentation, these are liable to change, so this can change. But yeah, so first of all, that ability to add points would be pretty nice. Add points, or we call it EC add, but yeah, this is the equivalent of multiplying in the multiplicative notation. Equivalent of that. Then there's also something called scalar multiplication, right? Which is what I mentioned, which is when you have a scalar value, and basically, yeah, how many times you should add a point to itself. Yeah, and then they have this multiple exponential. So basically, yeah, basically the same thing here, but
reiterating over the scalar module.
Exactly. So you have multiple points and scalars, and then you would kind of add, multiply, and then add them all points. So you end up with a new point, but still, yes, like multiple, just like speed up. And then this is the big one, right? Pairing check. So, and I know this is kind of weird because we end up with a 1 here, but remember, like, so you can imagine that. Oops, sorry, this is the recording for the previous.
Oh yes. Documents next.
Finished. So this is just, but you could imagine that we would take to the minus, something to the -1, and then so instead of having one pairing equals another pairing, you would kind of take 1 to the -1 and then flip it to the other side, so you get equals to 1 here. And I guess it would allow you to do
Oh,
this
okay,
kind of
okay.
product of pairings very easily. And then there's something called, another opcode will be the subgroup check, and that's a check if a point is valid. So not just that it's valid in the sense that it's not just a point on the curve, but it's also a point that's a member of the group that you want.
Okay.
Sometimes you want to check that before. So for example, before you just accept, like, if you're using a point to represent something as a public key, let's say, then you want to verify. You might want to verify in your smart contract that that's actually a valid point before you do anything with it. Then we have this really interesting EC map too. So this is a hash function, but usually a hash function takes some input, some concatenation of bytes, whatever it can be. It can be an entire file, whatever, right? You would hash it with SHA, 256 or something, and then you would end up with another value within like a finite what would you call it, like within some interval. But what this opcode will allow us to do is allow us to input a message, and then the message might actually be something that's been hashed and turned into a message. So it might not actually be but the point is that you can input something here, and then it will give you, this thing will give you another point. So it's not like you hash and then you get some value, some scalar, let's say. This will give you a point on the curve, right? And depending on which curve that you're going to use, then they have different methods for doing this. But this is very useful because.
Wait, so is it? Wait, just maybe noob question, but is this something that can relate to using hash maps or not?
No, hash maps are, you mean like the data structure?
Yes.
That's very. I don't think so. Like, not in this case.
No, okay.
I'll show you how you can use it. I'll show you, like, it can be used for ring signatures is very important, but also for I'm going to show you later BLS signatures, which are going to come next.
Okay.
I don't know if you got that far in your reading or.
The BLS part.
Yeah.
The BLS signatures. No, I had to skip for it.
Great. Then I have something to talk about. So pairing check is going to be very expensive. So we'll see. It might just be something that you do as a logic sig, or we'll see kind of how you implement it. But there are, at least in Barnes' example, he didn't use a logic. He used a stateful smart contract. But it's going to be very expensive, like more than 10,000 in opcode budget. But that's.
So 10,000, how much is it?
10,000 or something. I thought like 15,000 or 18,000. So that's going to require, if they can make it work for a stateful smart contract, it just means that it will be like more expensive. It will just mean like you will need a lot of transaction fees.
More transaction, yes.
Which is, I think it's not bad, because right now the fees in Algorand are very, very low, and that's because the blocks are like, if you look at what the capacity the Algorand blockchain has and what's actually being used, it's basically like, let's say there are like 7 TPS, right?
Yes,
or something
so
like
you can use more transaction to just, well, for one transaction you can use 7 and
exactly
fit in
more gas. You can say
yes,
exactly, and that's fine. Like, you might have, I mean, depending on what you're doing, like for example, let's say hypothetically, I'm not saying I would do this, but let's say someone created a mixer contract for private transaction, right? Maybe for a normal transaction you want 0.001 algo fee to send a transaction, but maybe you're okay with paying
paying more for more computation or more access.
Maybe you would, if you want to send 10 algos or 100 algos privately, you might be fine with paying not even maybe like 0.1 algo or something, or maybe not even that much, so just saying
I think it will be still because I think you can only adapt to 16 transactions, right?
Yeah, but there's some kind of trick that he was showing us where you can do up, and then you can somehow use because you know there's also inner transactions, right? So you can generate inner transactions.
Oh, okay. So you use, yes, there's
and that will connect. Yes,
150. Yes, yes.
But there was some trickery there, and hopefully we can cover it in a future topic or in a future meeting.
Sure, that would be interesting.
Yeah, but that's right. That's just the point, and I think that that's also why I feel like it's kind of also what inspired me to start this. Is we have a lot of really cool applications that we can use that can make use of, or something that we can create that can make use of all of this computation that's just lying around that's not being used. And
showcasing like the power of what you can do on a distributed computer.
You can do cheaply on Algorand. Yeah. So that's now we end up with, so this is one of the so this is an application you can use. Yeah, this is an application of signatures. So 15.5, this chapter or subchapter, it's called signature scheme from pairing. So I already mentioned the ED25519 signature scheme, which doesn't use pairings. But yeah, this is another type called the BLS, Boneh, Lin, Shoup signature scheme. And it's also known as the short signature scheme because you can use this to create very short signatures, but I'll come back to it. So here in this signature scheme, what you do is there's a key generation algorithm, which means that you generate a random scalar from this finite field, or from this integer field. And then you calculate your point, public key, from that by using the scalar mult or exponentiation. And then so the point here is that the public key is a point in G1. Pay attention to that, not a G0. The signature is going to be generated like this. You're going to use that hash to point function that I mentioned earlier. So this by itself is a point, and then you would do the scalar mult or the exponentiation in this case of alpha to it. So you would take this point, and then you would multiply it by itself alpha times. And so the signature for BLS is a point in G0. Okay, and then we have another algorithm which is to verify. Okay, so let's say I sign something. I have my secret key, which I keep secret. I have my public key, which I have shared with the world. Everyone knows it, right? And then I have a message I want to sign with my private key. What I would do then is I would take that message, insert it into the hash to point function, and then I would take that to the power of my secret key. I would share my signature, and so I would send my message, I would send my signature, and I would send the public key. And using only the message, the signature, and the public key, you can verify that yes, the owner of the private key was the one who
computed the message,
the signature, who has signed it. Okay. And the way you do it is by checking this pairing. So you do a pairing check like this. Okay, so why does this make sense? Well, this is what I mentioned. The reason why this makes sense is that if you look at it, if you look at this equation or this equality, the signature here is just h of m to the power of alpha, right? And the pk here, the public key, is just g1 to the power of alpha. So you start off here, you put in what pk is, with g1 to the power of alpha, and then because it's pairings, right, we can move over this exponent from here to here into G0. And so we move that over, and then we finally then we have the signature on the right hand. And of course, like, no one can see the world. This is what the world sees. They do not see alpha by itself, like in clear text. They don't see it. So that's why alpha is kept secret. But yeah, this is how you can do it. And so, okay, the advantage of doing this is that you get what's known as a short signature, because you only have 32 bytes, since signature is a point in G0. And so for ED25519, this is not the case. ED25519, you have 64 bytes, because you have this random value R, and then you have S. Well, I'll talk about that in the future. But so why would you care about this? Well, I think Dan, he mentioned in the presentation, right? He had this case where the government of South Africa or something, like the department for cars and you know the department that issues licenses for cars and stuff like that, they wanted very, very short signatures so that you could actually post them on the car, you know, or the license plates, or all, you know, or it could be the case that, you know, you have a game and you need, or some kind of software, and you need some serial code, right, to validate that this is actually a valid software, you know, and it's not been pirated or already bought. Then you might want something that's human readable or human inputable, and so there's an advantage of only having 32 bytes in that case. It's also possible, if you want, you can also flip this so that this, instead of the signature being short, it's the public key that's being short. But then, yeah.
But yeah, you're gonna end up with a long short secret key.
You're gonna end up with a short public key, because the public.
But
key,
if you flip it, you end up. Oh, okay. Okay.
Yeah.
So okay.
Exactly. So the secret key is always the same size.
Oh, okay. Yes. That was, I was wondering about that. So yeah.
No. Secret key is always the same size, but you can flip public key and the private and the signature key, or the signature. I'm not sure why would you want this. Personally, maybe there is some reason why you would want this, because I still think that
maybe to make it just more human readable, just maybe...
or actually, sorry, so you might want this, yes, where you want the public key to be short, but but yeah, we're gonna come to why, even though you can do something similar with ED25519, one thing that you can do with BLS is that you can aggregate your signatures. So I'm gonna come to that. I'm gonna explain how you can aggregate your signatures, but it means that you have many signatures, and then you can verify them all with just very few operations. Another thing you can do is called threshold signatures, which is where you have, let's say you have n signers, and then but you want, let's say you have 10 people, but it's okay if 4 people sign something, then it's fine. That's what a threshold signature is. You can also do what's known as blind signatures, which is where a signer signs a kind of encrypted message, where, you know, they don't really know what they're signing, but you can at least verify that as an outsider that the message itself has not been changed. It's still like the same encrypted value. And then it's also possible to distribute the secret key across several parties, and then add them all into an aggregated secret key. But specifically, we're going to talk about signature aggregation, because it's very simple. I think it makes sense. So given that you have a list of public keys that are members of G1, so these are the bigger points, and given that you have a list of messages, the same amount of messages as there are public keys, and then there's a list of signatures. So each of these public keys have signed. So PK1 has signed message 1 and generated the signature 1, sigma 1, and, you know, continue like that. We can easily aggregate the signatures by doing this multiplicative, or if you're using additive notation, it would be a plus, an addition, but here multiplicative addition notation. Yeah, sorry, maybe I'm being too repetitive about that. Maybe it's obvious by now what we mean.
No, but it's good to reiterate.
Yeah. So you can aggregate them by just doing this, by just combining the points to get operating them on each other, and you end up with a new point. So it has, you know, it says short here, but yeah, because it's, you know, this point represents all of these other points. The signature represents all of the signatures, but it's still the same size as one of the signatures. And then if you want to verify it, so instead of verifying, you know, the worst case is where you verify this one by one, right? So you for PK1, we're gonna verify that the message 1 was signed using the, you know, we can check with the signature 1, right? So instead of doing all of that, all of those things, you only check this, right? So you have, on one hand side, you have the aggregate signature, and then on the other hand, you have these pairing. Sorry. Yes. On the other hand, you have the signatures here, which are, wait, let me check. Sorry. Yes, this is a product of pairings. Yes. So here you have to
Okay.
take the pairings of all these and then sign. But at least you're doing it. Yeah, you're not kind of checking them like this one by one. You're able to aggregate them. And the reason why you can do this is because, yeah, I kind of have the, I put the equation here. So yeah, so you have the signature here, which is the same as this, right? And then you can break that off into a product of pairings, and then same way we can see that, you know, the signatures are just the hash of the message to the power of alpha. Sorry, this should be, this is a typo. It should be this one here should be, so it should be alpha 1, so the first of alpha. This is a typo here. I'm gonna fix that later. And then yeah, we flip over the alpha. Yeah, same here. It's a typo. Alpha.
Yeah, instead of E, there's only one. Yes.
Instead of alpha I, yeah, it should be an I there.
It's just
flip it over, and then yeah, we get that. So that's why that makes sense. They make clear in the point, like sometimes, you know, the aggregation it's not like a one-time thing, right? Where you do the aggregation once and then that's it. But actually, no, like you can do this continuously, right? Maybe once a week you aggregate a bunch of signatures. You just add them.
With which is the application you can do with it? So you can just compact data or something.
So yeah, I mean, if you want to sign, so for example, you have we can show. Wait, let me just explain this, and then we can actually go to the. You can go to the.
Oh,
book,
okay, the application one. Okay.
They have applications there. But like, for example, when you're having a certificate authority, and then you're trying different authorities that all have to kind of sign this one or different messages. You might like it. So there's this. They mentioned that there's this advantage. So there are some cases where the message is the same, right? So you have a bunch of authorities or different entities. They all have to sign the single message. In that case, we get this. What we can do then is since we only have one single message, we basically have what we can do then is you can just aggregate all of the public keys, like so, the same way we aggregated the signatures, and then we only have to do one pairing, right? In addition to all of these. Like, of course, this is, you know, this also takes time. But yeah, so that's the point. Like, this is like, you can aggregate a lot of different signatures and do it in one go. So that's like one of the advantages of using pairings and BLS specifically. There's a warning here. So this scheme, it is valid, but it's susceptible to this attack, which is called a rogue key attack. And that is like, okay, so let's say Bob is one of the people who's going to sign something. So Bob can be presented with this key that has it's kind of like the aggregate, but then kind of has removed, or sorry, like it's his key minus the aggregate, or has, you know, has had his key negated out of it, like in the way, how do I put this in a good way? But you know, like if you have, okay, let's say that Bob's value is 5, and then I take the aggregate, which might be 10, and then I take 10 divided by 5, or sorry, 5 divided by 10. Okay, now I'm just confusing people.
So wait, you take off the Bob signature, and so you can roll back, not roll back, like
So let me find it. So basically what you do is you would present a public key that has already taken into account Bob's, and it will basically, like when Bob,
then you make him sign it, and then you can,
it's going to make it look like Bob signed something that he didn't sign.
Okay.
So I'm trying to find, where do we talk? Where's this? Let me scroll. Oops. Sorry. I might have to edit this.
Okay.
Probably not. Probably not. It's more real like this, right?
Oh yeah, we can keep it in study mode.
Yeah. This is where they talk about. Can you see the book? Am I sharing the book now, or are you seeing something else?
Yes, it's the book. Yes, the book.
Yeah, okay, great. So here we have all the different security proofs for this. Yeah, here's where they mentioned threshold signatures, blind signatures scheme. Okay. This is the aggregate signature, how you aggregate them.
Mhm.
Here is the thing. Here's what they mention. So even though you have the aggregates for something, what you can do is you can remove a point that have this malicious version. Let's see. Yeah, this is the rogue public key attack. Oh, also, yeah, here's an application where the server S1 aggregates. Wait, no, sorry, that's not what I wanted. Okay, never mind that. This is the rogue public key attack. Consider a user Bob, whose public key is public key B, let's say, and the adversary wants to make it look like Bob signs a message, which Bob hasn't signed. And so what the adversary can do is they can create a public key adversary by choosing, just randomly generating a scalar alpha and then computing it. And then the private key corresponding to this public key is going to be it's going to be alpha minus alpha Bob's secret. Bob doesn't, like, the adversary doesn't know Bob's secret, and they actually don't know what this private key is. Like they don't know what alpha adversary is. They don't know what alpha Bob is. They only know what alpha is. Does that make sense?
I'm a bit lost.
Okay.
Connect it.
Yeah.
Okay.
Sorry for the third. Yeah, this is the third Zoom meeting now because we can't.
Yeah. It's actually, what is 40 minutes? 40 minutes. We're going.
Time is flying. So basically, what the adversary does is they generate alpha. So adversary knows alpha, and then they don't know the alpha of Bob, but they know his public. They know his public key. So they know the public key for alpha. They know Bob's public key. So what they can do is they can do this kind of operation that takes their public key here, and then they can do this kind of minus or division where they negate Bob's public key from their own public key, if that makes sense. And so the resulting, so even, this is what we come back to, this, kind of additive homomorphism, homomorphic encryption. So we're basically so alpha of Bob is encrypted in the form of Bob's public key. The alpha that the adversary generates from the beginning is also encrypted in the form of the public key U, but the adversary knows this. Okay. And so then they can generate this adversarial public key. So this let's say call it evil public key, PK adversary, which also has a private key, the alpha adversary, but the adversary doesn't know this one. Okay, they don't know this because they only know the public key, because they're able to compute from a public key they have and Bob's public key. They're able to compute this new public key, which so this is what we call a rogue public key. But the point is that the adversary doesn't know the private value that is behind
for the public key,
because they don't know they don't know Bob's private key. And so what can happen is that, and this is what they talk about, what can happen is that the adversary can compute, they can create an aggregated signature that makes it looks like Bob has signed M, even though Bob hasn't signed anything. Okay, and so the question then is, and this is invaluable if you're going to implement this. Otherwise, this is something to think about. There are two ways of addressing it, and one is to add something to the message, I think, to make sure that Bob actually kind of shows that Bob, kind of something from Bob, so that Bob is showing, yes, it was me, I was the one who actually signed this, or that it's to kind of disprove that, or to make it difficult, to make it look like Bob has actually signed it. Another way is to prove that, what's called proof of possession of secret key. And the point is that, like I mentioned, the adversary doesn't know this alpha adversary. They only know this simple alpha, which they generated. And so what you can do then is, well, you can kind of ask the adversary, well, why don't you sign something with this peak adversary? Why don't you sign something? Like, why don't you prove it to us that you actually know this value, which you would only know if you also know Bob's. So that's what we call proof of possession. So proof of possession in this case is by signing it with that key. Yeah. So they address this in the book. You can take a look for more details. But yeah, it's a row key attack. And this isn't just for BLS, but even for ED25519, if you want to do some stuff with it, like where you're adding 2 points together, and you, like I mentioned, what I was talking about with atomic swaps between Monero and Algorand. This actual attack also comes up, so it's always good. Like if someone is just in general, if someone is proving, if someone wants to include their public key, it's kind of like a good point to just tell them, well, sign something with it so we can be sure that you actually know something about, like, so you know something underlying about it, and it's not just kind of generated from other people's public key. And then after this is after this BLS stuff, the book starts talking about more advanced encryption schemes, and something called functional encryption. And this is where it gets very, very, for me, it got very advanced. And I think it can kind of, if someone's reading this book, like, this is it's like a lot of text, because they have a lot of different variants on this, and the security implications. But the point is, like, I think we can still go through, like, I can try to explain the point, like, what's the point of this. And so, and then, by the way, there's also something that Dan Boneh, one of the authors of the book, he was one of the people who he's been seminal in this field, identity-based encryption. So an IBE, identity-based encryption, is a scheme where it's a public key crystal system where any string is a valid public key. So in particular, email addresses and dates can be public keys. Okay, so what does that mean? Well, so this scheme, it does require that you have a private key generator. So you can imagine you can imagine a company, let's say. So let's kind of ignore the blockchain application here, but you can imagine, let's say you have a very large company, and they have some IT system, some IT, what do you call it? Some IT group within the company, and they own the private key, and then from the private key they can generate these kind of secret key parts, you can say. So they have the mass secret key, and then you have from that you can generate these smaller keys. They also mentioned in the book that even if you might, so if you try to take this out of the trusted setup situation, it is possible to try to distribute this master secret key across multiple parties, and then you might still be able to get the advantages of what we're going to talk about without this disadvantage. But they don't really explain how you would do it, but I'm sure it's out there somewhere. So the point is that, like usually, right, we have a secret key, a secret scalar, and then that's our secret key, and then we generate a public key from that, right? We create a point, and that is our public key. Well, and then, like, if people want to encrypt and send something to us, what they would do then is they would take our public key, and then they would use their private key, and then they would encrypt or something, or like, or they could just use our public key basically, okay, so the point is, they if they want to send something to us, they can encrypt something with our public key. But with identity-based encryption is that we can use our email addresses or any other thing as public keys. Like, it doesn't have to be that. And so the advantage is that instead of having to generate, like, each person having their own public key and then having a separate field, you can just use people can encrypt things and send them to you just using your public key. Just using your email address or some kind of string. So this saves database storage because you already store usernames, right? And then you can also have expiration. So let's say that, so Jacobo, I want to send something to you. I grab your user email, and then I concatenate with today's date, and then I encrypt my message using this, right? And then this private key generator, this master trusted coordinator, will send you your secret key for that day. Like, so they will send you a secret key that only applies for this public key. And so both them, of course, and also you are able to decrypt what I just sent you. Okay. And the secret key is gonna be, because when I send you the message, I'm gonna encrypt it with today's date. The private key generator has to send you a new secret key every day. So this means that, let's say that you quit, and in the future, maybe I don't know that you quit the company, and I try to send you something. Well, you won't be able to decrypt what I sent you because you're no longer in the company. You're no longer getting these secret keys every day. Does that make sense?
Yeah. That's very useful for maybe rotating keys in the company.
Exactly. Yeah. Yeah, and you can also use email subject lines as private key, public keys. And then for different labels, you can have different decryption keys. So different secret keys that are used for decryption. And so you can have a company with only one email address, but then depending on the email subject, different people can decrypt the message or not.
Oh.
So there's a paper by Boneh and Franklin. People can take a look from 2003 where they talk about this. But yeah, I'm sure there's been new stuff since then. And then later they talk about functional encryption paradigm. So if you think about the basic level, right? The basic level is that you have one key pair for encryption and decryption, right? It's either all or nothing. Either your secret, when someone encrypts something with your public key, either you can use your private key to decrypt it, or you can't, kind of, if they didn't use a public key, right? So it's all nothing. But then if you think about it, next level, well, with the identity-based encryption, we had a one master key pair, but then so the master key pair can decrypt and encrypt whatever they want. Sorry, they can encrypt everything that uses. They can decrypt anything, right? But then they can also kind of take off a chunk of that domain, and then they could package it and give it to you, right? So they give you a secret key that can decrypt something for a specific ID, right? So they kind of, it's not all or nothing. It's either all, nothing, or partially. You think of it like that. And so the idea is, well, can we generalize this and obtain a broader definition for public key encryption? And that's this idea comes from. And for me, this is like, this kind of took me a little bit of time to understand the broader picture here of in these chapters. But the idea is that you could generate a public key and a master secret key using a setup, and then you can generate what you can do then is you can generate the secret key that's a partial decryption key, right? And then you would encapsulate this function for that's specific to the secret key. And then when you encrypt your message, when someone encrypts with a message, then you're using the public key, but to get this ciphertext. But however, when they decrypt the message, when you, who has been giving this secret key, this secret share key, when you try to decrypt this encrypted message with it, you're not going to decrypt it like into fully ciphered clear text or plain text. You're actually going to decrypt it in this way, like you're gonna get the sorry, there's a typo here. I wrote X here and then I wrote M here, so this is supposed to be an
X. Okay, that's
my bad. So instead of getting X itself, you're actually gonna get back Y, which is a function of X.
A function of X.
Yeah. And so if you go back to this basic level, right, for the basic level where you have one key pair, the F in this case is just, the master key is the function, is the same as the secret share that you can generate. So there's only one functional secret key or private key. And the reason why is because F is the identity function. You can call it an identity function, right? It doesn't really do anything. It will decrypt any well-formed ciphertext. So anything that's actually encrypted will be decrypted. And then for IBE, there is this, the secret key ID. So it's a secret key specific for an ID, right? So for a string of any kind, specifically for your, your email address, whatever. And so people can use that, right? People can use your public key that's specific to your ID, and then you can send something direct just to you, and then you can easily decrypt that value if it's been sent to you. But then we can take it a step further, and or we can do some other stuff, right? So one way is to look at linear functional encryption, and that's where he mentioned actually, like, you can do this without pairings, but yeah, there's also a way of doing it with pairings. And so what it allows for is linear fitting on encrypted data. So what that means is that you can define a linear function, like, you have a bunch of points. This would have been nice with the graphic, but you can imagine like where you have a bunch of points that follow some linear, on a graph on X and Y. You have X and Y, and then you have a bunch of points that follow some kind of linear equation. But then there might be some noise in the data, so they're not going to strictly follow that straight line. They're kind of going to be dispersed around that straight line. So what you can do is you can do a linear fit, where you can calculate that linear function, that equation, that straight line that best fits the data, right? Does that make sense? Or does it sound familiar to you? Maybe if I or maybe there's some good linear regression. Basically, if you think about
okay, yes.
Yeah, I should have had this in the. But basically, yeah, you can imagine that there's some function, there's some underlying, you have some data, and then there's some underlying distribution of data that distributes data around this, and then we can do what's called linear fitting or linear regression, where we can compute this y equals, x times something plus some constant, right? And we're trying to minimize the error. So we're trying to create a line here that it minimizes the error, right? So there's going to be some error here for each point from the line that we're going to be creating, right? So we want to create a line that best fits this data, this noisy data. And we can do that using, with linear functional encryption. We can actually, if we have encrypted medical data, we can decrypt, we can allow certain researchers, let's say, access to certain points or a specific subset of points, and then they can get access to that linear function. I don't know if that makes sense.
Yes.
They can do linear fitting, linear regression on encrypted data. And the details are more explained in the book, but they also don't go into too much detail, like into super depth into it. There's also quadratic functional encryption. So so in the same way, so I don't know if you know how to calculate standard variance or standard deviation on data, but you're using basically taking the points and the data points, and then you're doing a quadratic, taking it to the power of 2, and then doing some stuff. And so you can use quadratic functional encryption to calculate variance and standard deviation on encrypted data in the same way. Once again, we have then there's something called attribute encryption. So attribute encryption, is very similar to IBE actually, but so instead of polynomials, so instead of this function f that we're talking about earlier, right? So we have we have input x. If you go back, we have input x here, supposed to be an x here, right? We encrypt it, and then we can decrypt it, but we don't decrypt it like in plain text. We actually decrypt it as a function of some value. Sorry, we encrypt it. We decrypt it. Sorry, we decrypt x and produce y, which is a function of x. So we don't actually get x with y. We're getting a function of it, right? So instead of polynomials, instead we have these predicate functions, which are basically 1 or 0. So you can think of it like an if statement, right? If something, then this is true. If not, false, right? So what we can do is we can have, it might be even more confusing because now I have X as an attribute and then we have M as a message. But instead, you can think of the data as having some kind of attribute and then U as having some kind of attribute, right? So let's say that you are, it's kind of similar like what I mentioned about delegation, but the idea is that let's say that there's some kind of attribute of the data where the data is has been encrypted. So let's say we've said that, oh, this data is category A. Let's say this is a category A data, and you are part of the A group. Okay, so therefore your secret key, because it belongs to the A group, and because data has been encrypted to have that the attribute A, you are able to decrypt that data, if that makes sense.
Yes, you can actually make it also for the like a role base or something.
Exactly. They mentioned this also, but yes, role based, right? So these are other examples of what you can do with pairings. I don't know how relevant they are for blockchain and stuff, because it is also about encryption and decryption, which it's not really something that you would like. You might, yeah, you might check the validity of something using a smart contract, but of course, smart contracts are public usually. So unless you're checking, yeah, I mean, you can always check the validity of encrypted data using pairings. But yes, I'm just thinking like how relevant is this for us in the blockchain space? I don't know. We'll see. We'll see what happens with this. But pairings has to do with pairings, so it's part of this topic. Finally, yeah, we talked about some multilinear maps. So if you just take a step back, right? So we talked about bilinearity. That's what pairings have. It's kind of pairings we have now, which we think is really nice, right? Could we generalize this, right? So instead of when we were talking about G0 and G1, what if we could have, up to Gn, right? Wouldn't that be nice? Okay, so why would that be nice? Where of course, where GT is a generator, it's not a degenerate pairing, but actually, it doesn't only and it doesn't just take it to the value 1, but actually gives you a generator for the target group. So this is an active field of research, and this is kind of, Dan was talking about this in his presentation as well, right? He's saying like it would be amazing if someone could figure out multilinear maps. It would be like this huge thing. So why would this be interesting? Well, secret sharing. So right now we can do secret sharing for 2 parties. So let's say that you have alpha, alpha, I know beta, right? That's Jacobo. You have this secret value, I have this secret value, beta. And so we can create a secret, this kind of Diffie-Hellman thing, right? Where I take your public key, right? I take your public key and then I use my private key on it, and then I end up with this value right here. Similarly, you can do the same thing. You take your public, you take my public key, G alpha, and then take your beta on it, and then we end up with this, right? Yes, you can do that with, and then we get the shared secret kind of thing. With 3 parties, we can do this. We can do with pairings. We can do it with 3 parties, right? Or we can take. So let's say you, once again, you have alpha, I have beta, and there's a third party, a third person who has gamma. Well, because you have alpha, right, you can take our public keys, and then you can add your own. You can take the pairing of them, and then you could take an exponentiation with your private key, and then you will end up with this shared secret that we all have, like so. But what about for 4 parties? Yeah, there's no practical solution. So that's something.
Is there a reason for that? You can.
I think it's very difficult to do it. I mean, somehow
I remember Boneh said something like for the multilinear maps that the reason that they cannot find the solution because it's either breaking the script log problem or finding with bad curves.
Okay, yeah. I think he said like there might be some cases where you can have some non-efficient solutions. I think I read that on Wikipedia. So you might be able to get, like, there might be some incredibly expensive versions, right? That's not really practical for us. That's why I wrote the practical solution.
Not easily contributed, yeah.
But getting, you know, more, it would be really nice, apparently.
Oh yeah, that's what he said actually, as I remember.
Yeah.
He said it's either you can, he in the search he was searching this part, and he was said the ones they were coming up with are either too hard to compute, or they would end up with ones that would be with easy solutions to the discrete log problem.
All right. Yeah. So that was the entire chapter.
Oh, we did it.
Yeah, that was basically what was mentioned in the chapter. Of course, in the chapter they have a lot of security proofs. They have a lot of these things. There's also a section for exercises. So I haven't covered that, and I didn't do this exercise myself. Maybe if I were a PhD, graduate student in this field, I would be doing them, but I haven't had the time. Do we forget something, do you think?
Wait, sorry, I just have to go check my dog. 1 second, I'll be back.
Okay.
Okay, sorry, I'm here. Can you hear me?
Yeah, I hear you.
Okay, good. Sorry, did you ask me something while I was away? I didn't.
No, I'm just wondering if we forgot anything. I don't think we forgot anything.
No,
or
I
unless
think
something
we went
we want to
over
mention.
the chapter. Not particularly. I think it was.
Yeah, we covered most of the things, and so the point is, I mean, now it's only us two here, but if anyone else is reading the book right now, and then they can come, they can come and they can watch this video, or you can watch this video before you read the book, before you read the chapter, and then you have, you've basically prepared your mind a little bit, so you understand like the bigger picture before you dive into the details. But if that's it, and hopefully if I've said something wrong, if some kind of typo, hopefully someone will tell me.
You can use the repo for that.
Exactly, repo, or I will edit something in the final video or something where I kind of explain like, okay, I got corrected on this. Yeah, I'm also an amateur here. But yeah, we're all learning together, so
yeah, that's the good of it. No.
Yeah. And then so then the question was like, what is the next topic? And I'm sure we will write in the Discord what the next topic should be, but I have some smorgasbord of inspiration. So if you're really
what's that?
Smorgasbord. It's like in English, say like smorgasbord. Smorgasbord is the Swedish. It means a table of sandwiches.
Oh, that's good. Okay.
But it's an English term. I don't know how it entered the English language, but
okay.
So another.
I never heard of it. So.
Yeah, I get you. Yeah. So there's something called lattice-based cryptography, which is another like. It's like we can call it a parallel field to elliptic curve cryptography, or a competitive field, competing against it. We use lattices instead of elliptic curves. So this is something completely different. And the reason why this is and actually in the book, this is actually this is chapter 15 that we just talked about now, elliptic curve cryptography. Chapter 16 is about lattice-based cryptography. So we could, if you wanted to, just continue with that. But I don't know.
Okay. Actually, I was also interested in maybe there was the. Wait, can you go on the others?
Yeah, I'll go through all of them. But I just want to explain like what is lattice-based cryptography. So we're using lattices instead of elliptic curve, and you don't have this, like elliptic curve cryptography relies on the discrete log problem, right? We assume that something is hard, But we know that in quantum computers, they can efficiently
we can break that easily.
Yeah, there's something called the Shor's algorithm, I think, which I guess not easily, but it kind of it just makes that much easier to break. And so there's this other field, lattice space cryptography, which doesn't suffer from that. It doesn't rely on the discrete log problem. And actually, the Algorand Inc.'s very own Professor Chris Pikert at is it University of Minnesota or Michigan? Anyways, he is one of the pioneers in this field, actually, and he's one of the people who's been part of the state proof. So in Algorand, we have state proofs, right? Which so we have this interval where let's say every n blocks we produce a state proof, which is a compact certificate of that kind of proves that okay, so all of these transactions happen in between these blocks, and a significant chunk of the stake of the people, the stake of Algorand, like the entities staking on Algorand, all agree on it. They all sign off on it.
Is there a threshold for how much is? Like, I thought it was more than the normal threshold.
I think So I think it's those things where it's kind of like how good do you want it? Like, do you want 70%? Do you want 60? Do you want 80%? Do you want? Yeah, hopefully I think we have 10 more minutes. Something. We'll see. I got the message again. But so it's one of those things where so I'm not sure if they decide on it, but it might be like 80% of the stake. The point is that all of the
the higher the threshold, the more secure the proof is.
Exactly. The more people have agreed on it. And so they invented something called Falcon keys, and these use lattice-based cryptography, and they're post-quantum. So when we say that Algorand is post-quantum proof, we're specifically talking about state proofs.
State proof, yes.
So if anyone, and there's something called learning with errors, and there's something here is called FHE. It's a field called fully homomorphic encryption, which is the idea that I mentioned before, right? You're doing math on encrypted values. And this has become a huge thing. We're still super early, but basically, now with ChatGPT and AI and stuff. So the idea is that can we use neural networks? Can we run neural networks on encrypted values? Right. So
for data privacy.
Exactly. So can I send, can I take my medical records, send them, encrypt them, send them to some company across the world, have them run their own FHE AI algorithm on that data, send me, produce some encrypted data, and then I get that encrypted data, I decrypt it on my end, and then it tells me, oh, I have this disease or not, right? So
sure.
Maybe we can save this for the future. I'm not too keen on this because it's very heavy and it's not like immediately relevant, but it's like kind of those, if we ever get tired.
I remember the Buff Network did a reunion on that. It's like a blockchain collab, the Buff Network, and they made meetups for about this fully homomorphic encryption. They were talking about also querying databases without revealing data. So that's actually an interesting field.
Yeah, it's interesting.
not exactly inside the blockchain, maybe.
Yeah, and we probably won't see this in the AVM anytime soon.
But
it might be something that let's say that someone who wants to improve Algorand, they might suggest something that can be implemented on the fundamental level Algorand, like not as part of smart contract, but on the software itself. But let's ignore that for now. There's also this idea ahead of like Monero tech. So I'm a huge fan of Monero. I know also John Woods is a huge fan.
I saw him. I was tweeting about.
So part of that is ring signatures, which I think I want to implement on Algorand. Not for my own sake, but if anyone else wants to do something with it, they could because you could use that to create mixer contracts, mixers. And they also use something called bullet proofs. So bullet proofs are zero knowledge proofs that prove that some kind of some encrypted value is between a range, right? So in Monero, you have private, when you have private so with ring signatures, let's say like on Algorand, like let's say I want to send you let's say I want to send myself, or I want to send privately 100 algos, right? If I use a ring signatures based smart contract, it would allow me to hide, to obfuscate who I am. Basically, I would hide my own identity in a crowd of other people. Okay. A ring signature basically allows you to sign, like let's say you have 10 people and they all have their public keys in the public. And this is like ED 25519. These are like standard Algorand public keys or whatever. They could put them there in the open, and then I could sign. I could create a ring signature, which is like a signature that says like one of these people, one of these 10 people or 11 people with me has signed off on this. But I'm not going to tell you who. Like you don't know which one of us, but one of us did it. But so using that, you can get that kind of obfuscation in a mixer contract. However, you will still see the amount of algos going in and out of the mixer contract. So what you would to kind of hide this is that you would say, well, if you're using this mixer contract, you can only send in 100 algos, and then you will only be able to take out, let's say, like 99 algos, right? So there's going to be some loss, or 99.9 algos, let's say, right? So that's how you sign it. But with bulletproofs, what you're doing is you're actually encrypting the transacted amount itself, but you're still proving that like between this block and this block, the total amount of Monero, right, or algo, if it was implemented with Algorand, has not changed, right? So there's still the same amount of algos in circulation, and I'm proving this with this bulletproof. But I'm not going to tell you, I'm still able to hide the exact algos or the exact amount of crypto that have been transacted. So that's a bulletproof. So ring signature actually is quite easy to explain, and I think it's going to be quite relevant soon.
Maybe we could go over that, either that or maybe it's the case next, or the one also was interested.
Yeah, bulletproofs are a lot more complicated, but it's also good to know. And then they can also tie into this general, ZK snark work, which is the rage right now. Groth 16 is what I mentioned. So a ZK snark, and by the way, Jacobo, I might run out of time soon, so be prepared.
Yes.
But,
okay.
A ZK snark is called zero knowledge, succinct, non-interactive argument of knowledge. So basically, you can prove, like I can prove to you that something is true, I can prove that I know something without actually telling you what I know. So I can prove to you that I'm a member of a group of people. So for example, if you take a look at a mixer contract, in a mixer contract, like I mentioned with ring signatures, you would send in money into a contract, and then you would want to take out that money from another account, another address. But you want to do it in a way that doesn't link your original account with your new account, right? So with Groth 16, what you will be doing is you would actually be proving that you're a member of the people who sent, you're proving that you have sent money into this account. And it's similar to what we were doing with ring signatures, but the difference is that with ring signatures, you're proving that you're one of 10 signatories, right? And the reason why you do it, and the way you do it is you actually list like the 10 signatures of the 10 public keys for these 10 people. With a Groth 16 proof, what you would do instead is you would prove that you know a path in a Merkle tree, which is very abstract, and I can explain it later. But basically, like you're proving that you know a path in a Merkle tree. So then you kind of you're not
without revealing the path. You can just say I know how to get there without showing the path. Exactly.
That's very, very abstract. But yeah. Groth 16 it requires what's called a trusted setup. So basically it's not a good way. It's like a negative of Groth 16, and also you can only have one circuit, so you can only create a proof for. But then if not, you have to have this ceremony where you create a new circuit. Plonk is different. You can use like universal circuits, but it's a lot more heavier. It's a lot more heavier to compute. So that's why a lot of people still use Groth 16, even though it's a trusted setup. So you would have this ceremony where a lot of people are contributing the randomness to it, so that you can kind of be sure that it's still like it's not like the trusted setup.
But just to understand better, how do you mean like a trusted setup? Would you mean
so a trusted setup means that like when you generate, you would have a prover key and a verifier key. So basically, like for the circuit, you're gonna generate some parameters, and you're also gonna contribute a random value, okay? And if you kind of have to, the point is that you kind of have to like to yourself, you kind of have to like remove these your own knowledge. You kind of have to delete these things, and then because if you still have them, then you can make proofs that are not true. Like you can prove that you know, like I mentioned, the path, even though you don't know the path, just because you generated this the zk snark, underlying stuff like the parameters, and so you can do so. It's called like toxic waste. You kind of have to throw it away, and then everyone around you has to believe you. Oh, okay, so Jacobo, we trust him.
Okay.
Promise that he deleted this data that so that's the problem. But what you should say, you would have something called powers of tau, where you have a group of people, they're all generating their own randomness, and then they're contributing that. And then if you have enough people, if only one person is honest and they have actually deleted the stuff from their computers, then you can go ahead and trust them. Plonk doesn't have that problem, but it's much more heavier to do. But yeah, so the thing that Barnji showed us, the demo, ZK demo, he showed us using the pairing check operation opcode. It was based off of Groth16, and also so we're back to recording once again. We hit the Zoom limit. So I was just talking about how Barnji and the DevRel team, they made this example repository where they showed how to use Groth16 with the new update, with the upcoming, basically, they're basically using a PR or a branch of the Go Algorand repository. So that's Groth16. I think it's very interesting, very relevant for us. He has some downsides, but at the same time, a lot of practitioners use it for so for example, like something like Plonk, maybe you could use it on an L2, right? Or you can use it on a new chain, but then maybe you can't. It's difficult to use it in an EVM contract or Algorand AVM smart contract. You would rather use Groth16, and then you would have to deal with the trusted setup using this what's called powers of tau. Another one that I'm super interested in, and this is actually what I was looking into before the study group. I was trying to understand it. It's called Casino. So there was this team of researchers sponsored by Cardano Foundation, IO Input Output Hong Kong, IOHK, and they created this line of research, you could call it, these different protocols called Real, Kaleidoscope, and 21. And so basically the idea is, okay, so let's say that you and I are playing, this is related to gaming. We're playing games. So let's say that we want to play Uno or something, or poker. So actually, Kaleidoscope is for poker. It's like a protocol for running poker. 21 is for playing 21. And then Real is for any kind of, it's like a general purpose protocol for any kind of card game. Because so let's say that we're playing cards, right? And we have to keep in mind, like, we have our own secret, like every player has a card of hands, right? Our hand of cards, I should say. Basically a secret state that only they know. And then there's also a shuffle deck, right? And the deck is, of course, hidden from everyone. Like no one can know what's the next card, right? So then, like, could we currently, when you look at Casino, like there are a lot of gambling websites, right? But they are typically centralized servers, right?
So on the centralized on a blockchain, you will have to basically break the secrecy of your hand to play it.
So the idea is that you would, and this is something that I've been looking into. We'll see where I go with it. I don't know if you would want to be included in that venture, but the idea is that you would have a software that you're running, and then you find, like, there's no centralized server. You just find some people you want to play poker with, let's say, right? So there's no centralized server. There's no one, because like gambling is like very online gambling is regulated, right? Like you can't, and you can't. For example, I can't be in Sweden creating a gambling company and then just like offering it to everyone in the world. I kind of have to check where the people live. Am I breaking some law somewhere? But the idea is, okay, well, but if I'm playing a game at home, right? If I'm playing a gambling, if I'm playing a poker game at home, like no one's gonna care, right? No one, like how would you regulate that? So the idea is that, well, what if we could use a blockchain instead, right? Like so I'm playing, so we have some, using cryptography, we can create a shuffle deck, and we can also, so a shuffle deck meaning that everyone has, so let's say we're 5 players, 5 players contribute to, all of them encrypt the deck, right? They encrypt each value, each card in the deck. And then not only that, but they also shuffle the deck. So they basically shuffle the 52, if you have poker cards, let's say it's 52 cards, right, in a deck, they all shuffle around those cards. And a lot of things can go wrong here, right? Like someone who's malicious could kind of add, can replace one of those numbers, encrypted numbers, with their own maliciously encrypted numbers, right? But you can use these zero knowledge proofs to not only prove that actually, the card that I'm contributing, or these 52 cards, they are the same cards as the ones before, only that they have been shuffled, and also that I have added my own encryption to it, right? I've encrypted with my own hidden randomness, and I also know I have proof of that, right? So we're doing these things with these, I call it casino games with hidden state. And so it would allow us to, you and me, Jacob, or anyone else in the world, to play poker, to play any kind of game, really. I would love to play. I'm a big fan of card games. I'm a big fan of board games too. So it will allow us to play these things. And then let's say that, to save computation and to get a better user experience, you and I, we would have, of course, because the point is that we're gambling, right?
Sure.
We're playing, with real money, just because. Then we would have a smart contract where we have our deposit and also the money that we want to play with, right? And let's say that they have to be equal size. So let's say that we're 100 algo that we're playing with, gambling, and then I have to add another 100 algo as my deposit. And so as long as I act honestly, I can win or I can lose my money, right? Or more money. I can win more money or I can lose my money. But if I start to act maliciously, if I don't follow the rules, let's say that you're drawing a card, right, from this shuffled deck of cards. Every one of us have to contribute, have to decrypt the value, okay? Until we only have you, until the only one who hasn't decrypted the card is you, right? And then you decrypt it, but you do it privately. And so you have, this is what it means for you to draw a card from this hidden deck, or this deck of hidden values, right? And so if I don't participate in that, if I'm just timing out, then that you could say, well, you can tell the smart contract, well, a player isn't participating anymore. Can you start a clock, right? And then the smart contract will sort of tick down. And then if I don't respond, then I would eventually have my deposit removed and everyone gets my deposit, right? So you can use this kind of punishment to make sure that people are actually following the rules. And then, of course, in the smart contract, you would check these ZK snark, or sorry, not ZK snarks. You would check these ZK proofs, or some called non-interactive zero knowledge. And there are different, like the Sigma protocol, there are different types of proofs you can do that aren't ZK snarks, that aren't like these huge, that aren't compressing huge things, but actually, doing stuff.
But I was just wondering, but is it already possible on Algorand since we have the randomness beacon?
So the randomness beacon, you can't really you can't check just using the randomness beacon is a great way to get randomness into your system if you want some agreed upon set of randomness. So for example, actually for 21, you see for 21 here, they actually say in the paper, well, we don't actually need all of this zero knowledge stuff. We can just use a VRF. A verified
yes, because you can just throw a random value for the next card and that's it.
Exactly. So exactly. Since it's public, right? In 21, everyone's cards are public, except maybe the dealer. But even then, so basically every time you pull a value, you're pulling a card from a deck, you're actually just running this VRF and using the randomness beacon. And so that's how you get your card. And then when it's time for the dealer to reveal their card, that's also what they're doing. They're drawing kind of, you know,
yes.
in the moment. So that's what 21, they talk about it here in the 21 paper. So you can actually already implement that. I know that there's a project on Algorand where they trying to do casino games and stuff, but I'm not sure if they're using, I don't think they're using this sophisticated stuff. So that's what
Are they on-chain? Is that on-chain casino or is it off-chain?
I don't know. Yeah, you're right. I don't even know if it's on-chain.
Because if it's on-chain, I think you can just cheat the game easily now.
Exactly. I think they might just be saying, well, we're going to use this public value and this public value, and
yeah,
and then you know, you can trust us.
So basically,
we are Doc's team.
Yes, but what they're saying with the study here, IOHK, is that so this ZK proof will make the end of each player hidden. At each round, you can always verify that the way I shuffle the hand, not the hand, but the way I'm playing my hand is always from the same deck of cards.
Exactly. So you can imagine, you know, instead of one person shuffling, you're kind of thinking, you know, well, I shuffle it to get deck of cards, and then I give it off to you, right? And then you shuffle it, but then before you accept it, you have to verify. I have to give you a proof that these values are permutated encrypted values of the same deck that we have from the start.
Yeah.
So in the beginning, it's just going to be like 1, 2, 3, 4, 5, up to 52. Like those are the values, and then I encrypt each one of them, and I also shuffle them. So I permutate, so what we call we switch values in a random way, and then I hand it off to you, and then you don't know, of course, already, like it's already been permutated and encrypted, but you don't trust me, so you're also going to add your own permutation and randomness to it, and then you hand it off to the next person with the ZK proof that you've done it correctly. So actually, I'm not even sure if this is possible. I'm not entirely sure if this is possible to do on Algorand, like with the gas. I'm not sure. I think it could be, especially when we get the other, you know, what I meant, you know, when we get the, maybe not the pairing checks. I'm not sure if we need the pairing checks, but I think with the other EC add and these things, these functions, especially if we can get it in ED 25519. Because then we can do, it was called like Peterson commitments, also part of Monero Tech. But yeah, so we'll get the
Monero King.
Something that I'm looking into. I haven't had time to look into it, but I would love to do something with this because for example, I play a lot of board games, right? So even same with board games, you have some hidden state. That's everyone is hidden from everyone. So basically, if we could get that to work, and maybe we would discover, well, we have these pieces of the puzzle, but we actually missed this one capability in Algorand. Then maybe we can go to Algorand Inc., the team behind it. We can say, well, if you would only add this opcode, then we can do all of these things. And then they might be like, okay, well, let's put it on the roadmap, or let's look into it, or maybe whatever, and then that would be interesting. So I think I'm very excited about this. Whenever I go out and play, I play Exploding Kittens with friends.
I love that.
I love that game, and I'm like, if only I could play this. Of course, not Exploding Kittens, but like the game rules aren't. Of course, the artwork is copyright, and you can't trademark it. But the game rules aren't. You can't. I don't know if you can even trademark game rules. But regardless, have that something like that on Algorand that you can play with people online, and you would create some kind of client for it, but then you would always verify it. I mean, you would have the smart contract in the background where if someone acts up, if someone does malicious stuff, so that's something that another topic, a field of topic that we could look into. Of course, we could like break it down different papers, but it's interesting to look into, and also introduces some proof of correctness of shuffles, or permutations, and some basic ZK stuff that isn't this huge step to ZK snarks. And then finally, yes, we have this other topic that I was thinking about, which is Algorand's foundation research into secure multi-party computation.
That one is actually what I also, because I looked into also Partisia blockchain. I don't know if you looked into the research channel.
No, I saw that you posted in the research hashed in the channel research, but I haven't.
I got a bit interested in their work on the multi-party computation. That goes a lot with the ZK, because they have don't remember the name, because they have different protocols. So basically on top of the layer 1, they have a privacy layer that computes with a multi-party. It uses multi-party computation to prove the enabled with the privacy layer. Yeah, maybe I'll go back to it and maybe we can talk about it, but it's very interesting.
I'll look into it as well, and I'm going to confirm if it's something similar to, for example, Zcash, who use, the people, Zcash they use like Zk snarks as well to get like separate, set of private transactions if you want as an optional thing. Also, like another really interesting blockchain, and actually John Woods participated in one of their events. It's Mina blockchain. Mina. What they're doing is they're creating recursive Zk snarks. So you could think of something like that for state proofs. If we can create because now actually looking into the the researchers at the Inc are looking into, I think they made some progress, is how can we make Zk snarks of state proofs specifically these
yes for the
can we
to make them verifiable on Ethereum, because otherwise
exactly, because right now they're not succinct enough. Like we have a compact certificate, but it's very compact to verify. Let's say you have 10,000 signatures or something, keys that have signed them, right? And then you need to verify. You can verify quickly with compact signature, but not quickly enough. So they want to create how can I prove knowledge? Not just that I can show you the compact certificate, but can I prove knowledge of a valid compact certificate or state proof, right?
Yeah.
And then can I convince you with that proof of knowledge instead? And that's what you could do with Zk Snark. And what Mina are doing is they're doing recursively. Like, can I, instead of showing you a valid blockchain history, can I show you proof that I know of a valid blockchain history?
Okay.
And then in the next block, can I show you a proof of proof? Oops. Once again, I got the recording finished. For last recording, it finished processing. So can I show you a proof of proof that I know? And so we get this recursive snarks. And I think my hope is that we can one day get recursive state proof. Like we can get like Zk snarks of state proofs, but then also get recursive proof of recursive Zk snarks of state proofs. And so, why would that be relevant? Well, let's say that you're using, let's say that you're a new node runner. You fire up your Algorand software, you pull down the Genesis block, and then you're doing catch up, right? So you're processing all of the blocks one by one. Eventually, you're going to get to the block height where we started using state proofs, So then instead of going through
each block, you can just go through each state proof, right?
Exactly. You can jump. I think so. You can jump to the next state proof, right? So we don't produce state proofs for every block, but I think maybe it's like every 256 block or something like that. Let's say. So then you're already skipping, right?
Yes, you should be skipping those blocks and just use
but then what if instead of doing that, what if you could, you can get a recursive snark of the latest state proof, right? So then what if I just give you the latest state proof snark, and then you get proof that from where I'm at right now all the way to the latest state height, the block height of the blockchain, as kind of stated by this person or this entity. Well, at least there's a proof here, a compact, a Zk snark that proves that this. So then you could basically skip like all the way to the front, and then you could.
But can't you just do it with the state proof? Because I thought that you can do it with the state proof. You can just skip from the Genesis hash to the state proof, or no? You can't.
Not from the Genesis. I mean, first of all, you have to get all the way to when we actually started.
Okay, so you have to get. Okay.
But then, so a state proof can take you to when a state proof was made, but you can't as far as I know now, we can't aggregate state proofs, right?
Okay.
We can't take let's say there's 1 million state proofs or something. I don't know, or whatever. Let's say it's 100,000 state proofs from when they were introduced to now, right? So at least then you're gonna have saved yourself. Maybe there were 100,000 times 256 blocks, right? So maybe you only have to instead of checking 25 million blocks. Okay, maybe maybe I'm exaggerated the scale here, but you can imagine like,
Yeah.
okay, so instead of checking that, you're only checking, let's say 100,000 blocks or state proofs. And then now instead of only checking, even checking 100,000, you will be checking one recursive.
Okay.
Sort of,
so
like
you
that's
just
kind of the magic of what we're talking about here.
so that will just make an instant catch up, no?
Yeah, and so I don't know if that's even possible. Like we'll see. That's something for the research. But that's the idea of
Yeah.
Mina blockchains. That's what they're doing. They're doing recursive, you know. And there might be some,
Okay.
of course, for Mina, there's like a trade-off, I think, which is the TPS. I think they have like a TPS of 20 or something. So like they can't really,
okay.
or something like that. I don't
Not
know,
that
like
scalable.
max. Yeah, it doesn't, you know, it's a lot of computation. Like that's what you're giving up.
Sure.
Or sorry, or we have to differentiate between prover time and verifier time. So if I'm the one proving that something is true, it might take me a very long time to generate a proof, but at least it will be very fast for you or
To
for
verify,
your smart contract to verify, right? So that's the problem, right? You know, creating these state proofs or these Zk snarks of this proof or whatever, it might take a long time for all of our hardware, like all of our nodes might require much better hardware. We don't know at this point, but at least for the next, you know, for some new participation node, it would be very fast for them. And then there might also be something with, I don't know, like with the recursive snark, I'm not sure, like there might be something with the trusted setup, or, you know, you might have to think about that, like how do you implement that? I'm not an expert on this. I would love to become an expert, and especially through this study group. But yeah, there's a lot of things to look into. That
we can pick maybe from Discord, maybe if you want to
Yeah.
wait. But I think that either Moneros or
can I just explain this? I don't think we can skip
Sure.
it. What is this? So what is this about?
True.
So this is about I kind of call it line of research, right? But they have created these. I even forgot what these acronyms stand for. I guess this is like committee as a service or threshold committee as a or something. So the idea is so the Algorand, what we do is we have this amazing thing where every block we have a committee of people. So let's say that you have, even if there's a million, let's say hypothetically, now there aren't, but let's say there were a million people contributing to Algorand, like a million participators, right? You will still only, in every block, you would every step, you would always have 1,000 roughly entities contributing, right? So a committee of 1,000 who are voting, right? If you know a little bit about how Algorand's consensus works, you have one person, or everyone is creating blocks. They're creating blocks, and then depending on who has, they kind of create a lottery ticket with their block, which, you know, depending on what you got, if you have the lowest value, then your block wins, right? And so your block has to propagate, and then eventually, if your block is chosen as the lowest value or as the lowest ticket, then that's what included. So we have this kind of soft block. We have the soft vote committee. So I'm a committee of 1,000 nodes or 1,000. Yeah,
validators,
1,000, right? And they get to vote.
I think it was 1,000.
Yeah, around 1,000. And it doesn't matter like how big Algorand grows. It's always going to be one. It's also always going to sample 1,000, right? And actually, these 1,000 are also self-selected. So they also select themselves by running the
VRF, yes.
And then they will choose, okay, this block here, that's the one that looks, you know, that's the lowest. And then we have a second step where we have a hard vote, and these people will actually validate, well, is this block valid or not? And then, okay, if it's not, then no, and go on. So okay, so what does that mean? It means that we're able to sample 1,000 people, and remember, these people are different each committee. Like it's not like okay, for the next 1,000 blocks or for the next 27 hours, these people are going to be the ones in these committees, right? It's not like that. It's like every time there are new members in the committee, which is amazing. Which is pretty great.
Also
so the idea is what?
It's also scalable because you can have like 1 million of nodes and still you always have the same size of the committee. So you don't need to like limit your committee, not the committee, like limit your validator set.
Yes, and in fact, we want as many as possible, right?
Exactly.
So okay, so what is so what's the next step? So the next step is after this that I've been looking into. Okay, so what if the committee members, like let's say that we have one person, a group of 10 people, they win, and then let's say they want to encrypt some value, right? So they encrypt some value, some secret, and then they want to pass it along to the next committee, right? So it's not so only for the winners. Let's say only for the winners. They don't care about the rest of the the rest of the world. It should be secret from the rest of the world. But as long the next committee are supposed to be passed the secret, and then they read it, and then they can pass it along to the next committee, right? So you always one of the papers is called "Can a blockchain keep a secret? Can a public blockchain?"
Oh, okay, I remember. Yeah.
Right. And okay, so and so they're exploring that, like how can you because people are going to be corrupt as well, like there's going to be some percentage of the committee that's going to be corrupt, right? And if you always have kind of corruptness each committee, right, like how many can you tolerate before the secret just gets destroyed, right? Or the secret no longer gets passed on. And so they're looking into those things. And okay, so why is this interesting for me, at least? I mean, I'm sure they have other reasons why this is probably this is like state-of-the-art research, right? But for me, I'm always interested in like, okay, what if we have like a DAO, and then what if the DAO can be in charge of, so now it's easy to have a DAO. A DAO will basically be like, let's say a smart contract which has an account, and then it can be an account of algos, right? And then you can have some kind of token, an ASA, that every member, so you're basically buying membership into the DAO by owning this token, okay? So that's easy. They can control funds, they can control other ASA, they can vote among themselves in different ways, what they should do with their with their stuff. But that's fine because it's within Algo. But what if Algorand? But what if, let's say that because especially for Monero, because Monero doesn't have smart contracts, right? So you can't do what we're talking about now, which is like bridging over to Ethereum, right? You can't do that. You can't basically pass along information. You can't have one smart contract sending something to the other smart contract. There's nothing there. But with Monero, in terms of interoperability right now, as far as I know, the only thing we can do is we can do atomic swaps. And even that, it's not really atomic. It's kind of like, but it's kind of this one, this kind of step, like kind of like a dance. You go back and forth, and then you can be punished if you don't follow the rules. Or if you follow the rules, then you have both you and the other person has swapped, right? But then you also need a person to swap with. You can't like swap with a smart contract that's always ready to swap, right? You have to find someone who's going to swap with you. But like, what if you had a DAO then that was able to store the private key for an account, or for crypto, if it's UTXO, like for keys, for coins, I should say, on a different blockchain. Like, what if you could do that, right? So then each block, each iteration of Algorand, you have a new committee of DAO members, and they're all, they're storing the secret, but then they're passing it along, or they're generating something new, right? And then so you kind of are able to keep along the secret. I don't know if what I'm saying makes sense, or if it's even realistic. But for me, like that's that's the problem that in my mind went when I started looking into this kind of research, which is how can how can we deal with that kind of interoperability?
That's interesting. I have a bit of a hard time to think about like keeping a secret, like what kind of application you can build on it. But yes, that one you described is
because okay. It's easy. Like let's say I have a DAO, and then let's say I have 20 trusted members of the DAO, right? And then let's say they're the 20 biggest holders of the token, and then we all just let's say that we all own 20 key shares of one public key and private key, right? And then we can do threshold signatures, or threshold signing. We can sign, let's say like 20 of us, or like let's say 10 of us agree, or 12 of us have to agree, then we can sign this thing. But then the problem is, okay, so let's say like one of us leaves, right? And then what do we do? Like, how do we update
how do you
that? It only works for so I'm wondering, maybe that's something that we could have, like a kind of updatable secrets that kind of somehow, I don't know if there's some way to update that, like every block or every I don't know. But that's maybe so maybe I'm like misrepresenting what the
What this
significance
study
of
is
the
about.
research is. But
Maybe looking into it, we can understand better what's the solution it's going for.
Yeah. And yeah, of course, anything else? That's the question. I mean, a lot of things you could look into. For example, there's a blockchain called Filecoin, right? And they're
Filecoin. Okay,
instead of proof of work or proof of stake, you can have proof of time and space. You can have all these different, those kind of things. That might be interesting for people to look into if you're interested in that. Especially, as we start talking about, as Algorand blockchain, as the blockchain history grows more and more. The problem is, of course, one is catch up, right? Stat catch up, but that's what we were talking about before. Like maybe with state proofs plus maybe something else, we could get incredibly fast catch up where a node can immediately go. They don't have to sync all of the history; they can just go to the top. But then even then, like, what if we? I'm getting a warning now, but like, what if we have, we have archival nodes, right? So we need to incentivize archiving. Right?
Yeah.
So we might be happy with only a small subset of really nodes having archives of the blockchain. And Algorand is also different because participation nodes don't need to remember all of Algorand. They only need to remember the last 1,000 blocks, as well as the current state of accounts. Like they don't need to know what happened, in 2011, let's say. They don't need to know that. But we still want to keep
that. There's one thing that's actually interesting about this, but it's also the state bloat. But
yes,
it's not only about the archival, not only archival, but also in the execution layer. Because if you have like a lot of accounts with a balance, you have to compute maybe each account operation during a block. Maybe if you don't have enough computing power, you cannot participate in that consensus round.
Yeah, I get you. So that thing is that is limited by the minimum balance requirement. So for example, when you create a new ASA, right, or a new account, you have to seed the account with 0.1 algo, right? So that's the point, is that you can create a billion accounts unless you have 100 million algo, right? And that's kind of what the deposit that you have
to do. But still, the other requirements will grow up in time.
Oh yeah, but I don't know, like for them to grow, I mean, they would really have to.
Okay.
They would really have to so let's say that we lower the minimum balance requirement by a 10th, right? So let's say that Algorand, the value of algo went up like 10x, right? And then we don't want one account or one ASA to cost 10x what it is now. So let's say that we take so instead of 0.1 algo, it might be 0.01 algo, right? But then we're kind of also reducing. Then we're basically saying, well, the potential storage that you have to keep for the current state has increased by 10x. I don't think that's an issue right now, because like I said, like state can change. Like it, it's you could remove, like I can delete my account and then people no longer have to care about it. But blockchain history you can never remove.
True.
Right. So in that case, that we might be interested to look, okay, well, how does, what about something like Filecoin, or what about, something where, how can we incentivize archival nodes to store larger and larger amounts of data? Like, how can we pay that, how can we kind of incentivize, right? Like, what if you need 10 terabytes to remember all of Algorand state? You don't need it for the participation node, but what if you need
just for the archival?
Yeah. And I don't know, like, so then you have to ask yourself, because I think the point of a blockchain is that I really like Algorand's way of doing it, because you don't have to store, right? So this idea of like, what if,
you can
like, do I need to know, like, if I go to Italy, do I have to, I just take out euros and I pay. I don't need to know, like, from ancient Roman times. Oh,
you don't have to go way back from where the first.
I don't have to know, like, oh, this person, in the Forum Romana, like they bought tomato, or not tomatoes, they were but that's kind of the equivalent, right? What we're talking about. If you don't, you can't separate those two. But yeah, so I'm just throwing something.
But you still need to have enough archival, like honest archival nodes.
Yeah,
in case of
like a new unless you create some new Genesis node or something, or Genesis block, and then say, well, I don't care about the first Genesis block. I'm only gonna care about the one from 2022 or something. Something like that. So we'll see how that goes. But yeah, so that's another thing that we could look into. But yeah, yeah, it's up to what
Wait, so you can I was wondering like you can just have an hard fork of people just pointing to a new Genesis block and just
So I think,
and then the new Genesis block is just like a state proof of the old blockchain. So you can just start from zero, but keeping all the proof of the like a compacted proof of the previous blockchain as a Genesis block.
Exactly. You could keep like a hash, right, of the previous block,
Yes.
and that would,
Yeah, basically like a roll up each time. You build a roll up in time. You don't scale with.
I think the one thing that kind of I asked John Zanotti about this, and he said that actually, like, so the Genesis block matters because every block has it listed. So then we would need some new way of, like, I guess we would all have to reach consensus. Okay, like this block here is going to be the new Genesis block, and then we're just going to accept, right? So if we all accept it, then we can update our current Genesis, because that's also a problem. Like, you know, like let's say I just take my Algorand node, and then I don't know about the Genesis block. I just download. Let's say I just say, okay, well, Jacobo, you have an Algorand node. Why don't you just send me like a copy of your database, and then you send it to me, and then I jump in, I link into the relay nodes, and then I get sent like all these blocks, and so I have to know, like, how do I know that these blocks that I actually connected to a valid Algorand relay node network, right?
Okay,
it could
so
be
you
like
use the Genesis
Algorand clone. You get what I mean? Yeah. So then you would kind of trust them because they would have that Genesis node at least.
The Genesis hash. Yeah. Okay.
But then
but if you add fork, you can agree. You basically agree on this new Genesis, right?
Yeah, exactly. So that could be something like, I mean, that's one way of handling it. I think, yeah, this depends on like which what kind of, and it depends on like what kind of application you're into. Like there's some applications that require data, you know, for data archival. For example, if I want to prove, I mean, a lot of stuff, like for example, you know, like these days, sadly, there's a lot of war going on, a lot of genocides, a lot of people being sent from their homes. Maybe you would create some kind of, you know, commit. Maybe I would say, well, my name is so and so, and I used to live here, and then I put it in, you know, into the Algorand
like a
transaction, and then I just send it into Algorand blockchain, right? And then it gets stored in, you know, forever in the blockchain history, and then and then, you know, maybe in 10 years I'm gonna be like, well, look, I made this, I had this transaction here, I made it 10 years ago, like, but then if you create a new block, fork. But yeah, so
I saw from the white paper of Algorand, there's also the vault thing.
Data sharding. Yes.
Data sharding,
yeah. No, that you're right. Yeah, and that's something that we're looking into. I heard that they kind of for as part of fast catch up and stuff like that. And then I think they're looking into. But I think I heard different things from different people that it's kind of like overkill for what they want right now, for what's needed right now.
And yes, we don't have that much. Yeah. Okay, bloat.
Yeah, but that's also something. Yeah, also something like we can look into if people want to read, you know, the old papers, the old Algorand papers. But yeah, so it's up, you know, your imagination is, if you can think of something, suggest it. I think there's a lot of interesting things, and I think, like, if we could create, like, my dream would be if we could have, like, let's say we have like 20 developers, right, of Algorand developers who know all these things, right? And then they're all, you know, working on as contractors, consultants, creating their own blockchain stuff, right? And then like what kind of moat would that be for Algorand, right? Because it's easy. It's easy if you have a simple blockchain. It's easy to get someone who has basic developer skill. Maybe, you know, they know JavaScript. They can set up a web page. You can create your wallet. You know, they can create some very basic smart contract. But what about these really cool, you know, what about these really cool applications? Like, I would love it if we had a group of people like that.
Yes,
that's the ultimate goal. So
maybe community wise, I mean, because I bet that at the Algorand Inc. they already have this.
Of course, they have the best.
They have the best. So. But yes, I think the goal for the group is to attract more community passionate people that want to apply that knowledge into applications.
Yeah.
Yeah.
So
Yeah, that's it for I think.
I think
Oh,
that's like
there's
it.
more. Oh, okay.
References. Yeah, I have
References
like a small, just yeah. Dan Boneh is basically he's awesome.
everywhere.
Everyone's watching. I really recommend. We really recommend that you watch it. Yeah, he's really like educational. He's very pedagogic, like
Mhm.
explaining things very well. I love like his presentations. He's a
Mhm.
great person.
Yeah, I followed both his courses.
Yeah, there's also a mock right now going on at Stanford, which is where Dan Boneh is, and also with Berkeley, which is where Shafi Goldwasser is one of
Mhm.
Silvio's research partners. So yeah, but that's the end for now. Yeah, this was awesome. Thanks, Jacobo. I hope this is the start of something
Thank
great.
you for the
That's good.
presentation.
And then I
Very
hope
good.
if you want, I hope for everyone watching, like you can go through the book again, right, and check the pairing stuff again.